This video is sponsored by Squarespace. Create a beautiful website without having to write a single line of code. By now, you've probably seen that beautiful image of the planet Neptune taken with the James Webb Space Telescope. When I looked at it, I thought to myself, wow, it's Neptune, but it's in the near infrared, so it kind of looked at once familiar and alien at the same time. I guess that makes sense. We are seeing it in the near infrared, but not being a planetary scientist, I wasn't exactly sure what to make of the image or how to interpret all the crazy features we were seeing for the first time. Fortunately, though, my friend Dr. Heidi Hammel happens to be the interdisciplinary scientist for solar system research with the James Webb Space Telescope, and she's using it to study the outer planets. Now, this image taken by Webb was not actually part of Heidi's program, but rather it just happened to be visible to Webb over the summer, so somebody at the Space Telescope Science Institute thought it would be a good idea to take its picture as part of its early release observation program. So even though the image was not strictly intended for science, there's still a lot of new information that it's revealing to us for the first time. And Heidi was kind enough to sit down and break it all down with us. We get into why the rings appear the way they do, what those strange bright atmospheric features are, some new features that have never been seen before, and why its moon Triton appears so much brighter than Neptune itself. It was such a fun conversation, and I hope you'll enjoy it as much as I did. And so I give you Heidi Hammel and Webb's exploration of Neptune. So Heidi, how does it feel to finally see Neptune through the eyes of Webb?
Well, it's been a long, strange trip, as you know, more than 25 years in the making, I would say, but it feels great. I joined the project that became James Webb Space Telescope because of Neptune, because I wanted to see Neptune with that next generation space telescope, which is what it was called back in the day. And so here we are, more than 20 years later, and the first images, they did not disappoint. Boy, they were spectacular. I was so happy.
They really are. And the first thing that just blew my mind about Webb's Neptune image is the rings. To see those rings again, that one must have been something that you must have been expecting to see. But at the same time, it must have been just such a huge trip just to actually finally see the rings. There they are, right?
Yeah. I mean, to me, the rings, I was planning for the atmosphere. I knew we'd see the rings, but when I saw the image, the rings were it. I'm like, that's it. This is the image. These rings are the story because they were just so crisp, so clear. You could see the faint dust bands, and I had not seen that since the Voyager flyby in 1989. And we tried. I mean, this is not for lack of trying. We used the Hubble Space Telescope. Our teams used the Keck 10-meter telescope. And we are barely able to see enough of it to write papers about it. But never seen a view like that since Voyager. I was yelling in my house. I'm like, oh my God, look at these rings. Getting my mom, my kids, my cats, hold my cats up. Look at the rings.
Well, you're right. Those Voyager images, even then, for Voyager to glimpse the rings, didn't it have to take like really long exposures that were just full of noise and stuff? And
yeah, it was tough because the rings are quite faint. The reason they pop out in our Webb image is because the planet is pretty dark, relatively speaking. Even in the near infrared wavelengths, there's a little bit of methane in Jupiter's atmosphere, and that methane is a super strong absorber of light. And so the planet gets really dark, and that allows those faint rings to pop out and be quite visible. But even for Voyager, it was hard. They had to do really tricky exposures with a very fast-moving camera that wasn't designed for the low light levels out at Neptune. So it was really a triumph of Voyager to get the ring images that it did. And for Webb to come along and just, la-di-da, let's just take a few minutes exposure. Boom, there's the rings. I mean, it just tells you the power of the James Webb Space Telescope.
It really does. And you mentioned that the rings are faint, and that's, I guess, because in part because it is much further from the sun than, say, Saturn's rings, but there's more to the story than just distance, right?
Sure. The brightness has to do with the reflectivity of the tiny little particles in the rings. And they're gray, we think. One of the things we'll be doing with our James Webb Space Telescope data is we'll be looking at the wavelength dependence of the scattered light from the rings. And with some of our later data, our science program, when it takes place, we'll be looking at mid-infrared data and seeing if we can see thermal emission from these rings. Even though they're very distant and very cold, JWST is designed to see the coldest, faintest galaxies in the universe. So the rings of Neptune are a piece of cake in comparison.
So one question I had about the rings is, I remember you were talking about Voyager earlier, and I can remember that there was some thought that perhaps Neptune didn't even have a full set of rings, that maybe it just had some partial rings or something. But clearly in the Webb image, we can see there's no question about it. Those rings are 100% intact. How did we go from ring arcs to what appear to be completely fully formed rings?
Yeah, well, let's take a step back and ask why people thought there weren't complete rings around Neptune. And that story goes all the way back to the planet Uranus, actually, when my colleagues, Jim Elliott, Ted Dunham, Doug Mink, they were looking at Uranus and they were trying to study its atmosphere as the planet moved in front of a star. And they were going to look at how quickly the starlight winked out to use that to model the atmosphere of Uranus. But being good scientists, they set the program up several hours ahead of time. So they were watching the star as Uranus was moving in, and it winked out. It disappeared a couple of times. And they thought, oh, something's wrong with our data. What's happening here? But they let it go. And then as the planet went out the other side, the starlight winked on and off again. And what they had discovered was the rings of Uranus blocking out the starlight. It was symmetric on both sides of the planet Uranus. And so everyone's like, well, let's go see if Neptune has rings. We'll apply the same technique. And so there was a campaign to look at many stars as the planet Neptune was crossing in front of them. And the challenging part for Neptune was that sometimes starlight winked on and off, but not on the other side of the planet. And other times, the star in a different place, it would wink on and off. And so people are like, well, there's not complete rings. There's clumps of ring material because it couldn't be moons because of just the mechanics of how it winked out, right? They knew it was a moon, but it didn't seem to be complete. And so that was where this term arc, ring arcs, comes from. And what Voyager discovered when it got to Neptune, in one of those images, you can see very clearly a complete ring, but really bright areas in the ring. And those are the ring arcs. So it is a complete ring system, but there's just thicker areas. So let's now go back and talk about what JWST saw. The question that is in everybody's mind is, can you see the clumps? Can you see the ring arcs in the JWST images? And I will share with you that in the composite color image that we put out, it is quite difficult to see the ring arcs. When you go back to the original individual images, we do think we can see areas that are brighter than other areas. So we do think that the ring arcs are there. One of the challenges is that they're kind of the main ring arcs are kind of close to the planet right now.
Oh, I see.
And so there's a lot of scattered light in these images from JWST. Let me take that back. There's not a lot of scattered light. That's why we can see the rings.
Right.
There is some scattered light, and that makes it very difficult to pull this out. I think what's going to happen is we're going to work more carefully with these images, the individual images that went into that color composite, and we'll do some more detailed processing, maybe some image deconvolution where we try to take out some of the scattered light from Neptune and pull out the ring arcs. And I think we'll be able to see them more effectively then.
Hello, my friend. We're going to continue our conversation with Heidi in just a moment, but first, I'd like to thank Squarespace for sponsoring today's video. Squarespace is designed to give you everything you need to create a beautiful website without having to write a single line of code. To get started, simply choose from one of the many mobile responsive templates and use their suite of built-in tools to upload your content. I'm building a new website for our annual workshop for writers, and it's amazing just how easy and intuitive it is. With its new Fluid engine, I can move and resize elements and know that they're always going to line up with the overall layout of the site. You can add any type of content, whether it's photos, videos, newsletter signups, e-commerce, or virtually anything else you can imagine. Connect your social media accounts to display posts from your social profiles right on your website. Setting up an email list is a breeze. You start with a template, apply your brand assets, and you're on your way. Even better, the responsive designs will look beautiful on everything from the largest monitors to the smallest phones. If you want to check it out for yourself, just head over to squarespace.com/launchpadastronomy for a free trial and save 10% off your first purchase of a website or domain. You'll find that link in the description below.
Would this be something that would be easier to notice in the mid-infrared? I mean, these are all near-cam images, so they're all taken in the near-infrared. What features of the rings, and indeed the rest of the planet, would you hope to be able to see with MIRI?
Well, we've never taken any mid-infrared images of the rings of Neptune, so we don't know what we're going to see. That's the excitement of science with a brand new instrument. I could speculate, but I'm notoriously bad at speculating. Going to see. I mean, I have ideas and they're usually wrong, and that's good because it means we learned something. So I don't even want to speculate. I'm just going to wait and see what we see, and then we'll put that whole story together after we get the data. But I'm sure it's going to be interesting either way.
Well, apart from the spectacular rings, and I agree with you. To me, when I saw the image, the rings were it. I was just like, oh, there's a planet there. And then I started to look at the planet, and now it looks like we do see a little bit more scattered light, but we see a lot of, well, I don't want to call them hot spots, but these very bright regions. Are these storms? Are these weather fronts? So what do you suppose they might be?
Yeah, so we actually have a pretty clear idea of what these things are because we have a lot of near-infrared images of this planet from the Keck Observatory, from the Gemini Observatory, even from the Hubble Space Telescope. So we've seen this kind of cloud structure on Neptune before. I just want to share a little bit about why we see this scattered light. Mm-hmm. If you've seen any of the web pictures, you know it has this big point spread function, we call it, like the spikes that you see coming out of a star. And every cloud on Neptune has a diffraction spikes coming out of it. And some of those clouds are really, really bright. And so they actually do have big diffraction spikes. But it isn't just a point. It's like extended cloud or a little band. And so your point spread function, your diffraction spikes are smeared out in a funny way. And that's what gives you all of that hazy, murky glow. It's the point spread function of the individual features on it. Well, there were some things we saw, though, that we hadn't seen before, some things that so were pretty interesting. If you look super carefully at the zoom in of the planet, there is a really thin, narrow line at the equator of the planet. And we hadn't seen that before. That was a surprise. And I remember talking with Naomi Rowe-Gurney, who is helping to analyze these data. She's a scientist working at Goddard. And she said, that's got to be, atmospheric circulation that's like, descending at the equator. And I'm like, we've never seen that before. She's like, yeah, but I'm sure that's what I'm like, wow, that's new. So that's new. Also, if you look very carefully, you'll notice that some of those clouds have a little bit of a bluish tint and other clouds have more of a yellowish tint. And what that tells me as a longtime observer of Neptune at these near infrared wavelengths is that those clouds are at different altitudes in the atmosphere. because different wavelengths, we have, this image is a composite of 4 different infrared wavelengths. And so a cloud that only reaches a moderately high level is going to be fainter at a longer wavelength of light. Only the very highest altitude clouds are really bright at the longer wavelengths. So as an example, there's a cloud that's kind of down around 5 o'clock, if you made the planet a clock. And that one is at pretty high latitude. We've seen that feature before. We have a name for it. We call it the South Polar Feature. It's not at the pole, but it travels around the pole. And it gets really bright sometimes, and then it fades, and it gets bright again. In these images, it's the brightest cloud on the planet. In fact, it's so bright that at some of the wavelengths, it saturated the detector. It got so bright that the detector said, I can't accept any more photons. And it kind of shut down. So that's important for us to know for our science observations. We're going to have to be very careful to make sure that we don't have very long exposures, because we now know that some of these cloud features might overexpose at certain wavelengths. So that one's more yellow. And then blue, that tells me it's a much higher altitude feature. And so, just a regular...
So the bluer the higher, right?
No, the yellower the higher.
The more yellow the higher. Okay.
Yeah, that's right. Because it's if you only see it at the blue, that means you're not seeing it at all the longer wavelengths. So, it's just one of these things. As a scientist who studies Neptune, I see that and I immediately think, oh, look at those interesting altitudinal differences. Whereas someone else is looking at it and just goes, well, they're just blue and yellow.
Oh, pretty colors. Yay. Right. So
people ask me, well, why isn't it blue? I thought Neptune was blue. And I'm like, yeah, but these are near infrared wavelengths.
Right. These are colors that by definition we cannot see.
Right. That's right. So we don't get the colors that we get for the planet Neptune, because that's the visible wavelengths is where it's really blue. So these are near infrared wavelengths. So there's a lot of rich science for the planet. And really what's coming, this is just picture data. This isn't even science data. What our team's science data is planning to do is actually extend this imaging out into the mid-infrared.
No boy.
Is really going to be very exciting. We're going to be doing spectroscopy all over the planet. So, here we just sort of have colors, red and yellow, or blue and yellow. When we do the spectroscopy, we'll have all of the wavelengths of light, and we will be able to do detailed atmospheric models of the chemistry of those different cloud features and those different regions on the planet. It's just going to be a bonanza of science for Neptune. I'm just so excited about it. 20 years waiting and seeing it work. It's great.
All that.
I know it would work, but it's one thing to know, oh yeah, it's all going to be great. And actually have the data in front of you now and actually start looking at it. That's just it's just hard to express how exciting that is.
Well, I knew that I wanted to talk with you about Webb's observations of Neptune, and indeed the other planets of the solar system it's imaged so far. But you had a perfect tweet that summed it up, and your reaction to seeing Neptune through Webb. You said that you ugly cried when you first saw this, and I could totally imagine you doing that. Yeah, you're doing it now. Almost.
Oh, there it is. Oh my God. Seeing my images. Oh, yeah, it was very, very exciting. And almost every image, or even spectra. I mean, I know the public doesn't really geek out on the spectra like we scientists do.
Yeah, sure.
When we see some of these spectra, I'm just like, oh,
yeah.
So cool.
Spectra is exciting. I a good friend of mine shared a quote with me. He said that a picture can be worth 1,000 words, but a spectrum is worth 1,000 images. And that to me is just a wonderful description, because spectra just tells you so much more information. I can't wait to see spectra of Neptune. So we also, this image that is getting all the main attention that really shows off the rings, that's just a crop in of a nice wide field image. And what we find are the moons and a particularly bright star But that's no star.
That's no star. That is, in fact, Neptune's moon Triton. And the reason it looks so bright compared to Neptune is twofold. One is that, as I mentioned earlier, Neptune is really dark at these wavelengths. Right? The methane in Neptune's atmosphere just sucks up all the reflected photons. And so the planet goes dark. But at the same time, Triton is a really bright moon. This moon is covered in ice, and it reflects like 70%, more than 70% of the sunlight that's falling on it. So it's just an incredibly bright moon. And so you have the bright moon and then the planet appearing darker, and that's why you have this apparent mismatch, what looks kind of strange that the moon is so much brighter. This is a function of the wavelengths that we look at. And this is part of what people are going to have to adjust themselves to looking with the James Webb Space Telescope, looking in the infrared. Things don't look the same as they do at visible wavelengths.
Sure. Yeah, and to think, it took me a while to understand this as well. I was like, why is this so? Oh, yes, that's right. The albedo is one of the highest in the solar system, I suppose. And I just couldn't believe just how shiny it gets at infrared.
And I'll tell you, it's got those characteristic spikes because this moon of Neptune is so far away from the telescope that you're not really going to resolve it. You're not going to see, surface features per se. I've been talking with some folks who think they want to try to do what we call deconvolution. It's a really beautiful point spread function. And one of the superpowers of James Webb Space Telescope is that point spread function, that those diffraction spikes are extremely stable. And so we might try to pull out some kind of spatial resolution on Triton, but we're going to be talking about like 3 spatial elements, like maybe a north and a south, which would be cool because if you ever show look at the Voyager images, the South Pole of Triton is really bright and different and unusual. So we might pull some of that out, but really what we're going to be learning in our science studies of Triton is not images, but we're going to be doing the spectroscopy. We're going to be taking that beautiful light and spreading it out into the beautiful rainbow of infrared colors and pulling out surface composition and looking at how that may have changed over time. Triton is an active world. It is a moon that had, during the Voyager flyby, active volcanic activity, cryovolcanoes, jets of material spewing out into its thin atmosphere. And so there's a possibility that its surface composition may have changed over the 30 years since Voyager. And so we'll be looking at that. It'd be very interesting to find out.
Wow, to glimpse some of the evolution of a moon of Neptune, or some, maybe, if not evolution, to see some seasonal perhaps changes. That's just incredible.
Yeah, and there's an even wider field view that shows Neptune and Triton in the context of the galactic field in which it is placed, which is just as amazing to me as our close-ups of Neptune. I mean, being a Neptune scientist, I always say, zoom in on Neptune. You got to zoom in. But pulling it back where you can actually see the galaxies all in the background, that just about everything you see behind Neptune and Triton is a galaxy. There's an occasional star that pops in, but all those other speckles are galaxies. We worked hard on the Hubble Space Telescope to get a deep field like this. Here, it's just taking your pictures of Neptune. Oh yeah, you get a deep field just as a bonus.
It's like Oprah Winfrey going, and you get a deep field, and you get a deep field, and it's just like there's deep fields everywhere. Oh my gosh.
And, I think too, people should appreciate that this picture is focused on Neptune. And so it was tracking Neptune.
Yeah.
Right? And Neptune moves pretty slowly, but it moves. And so having that capability to the James Webb Space Telescope to track that moving target and get such exquisite images of the rings, all those other galaxies that you see there, they're a little bit smeared out because we're tracking Neptune.
Oh, yeah. Yeah,
You know,
I hadn't thought about that, but you're right. We don't see the spiral arms.
and some of them you do. If you go like
Some of them,
down,
yeah, maybe that one a little bit.
one down in the bottom, sort of the bottom left, and it's got a real nice. There you go. The
There it
beautiful
is.
structure. But I just want to share, when we do our actual galactic deep fields, we will not be tracking on Neptune, and so even these images are going to be even sharper,
Yeah.
and crisper and deeper. It's a. I think what what I take away from this is it an image like this shows you how our solar system is placed in the context of all the other galaxies out there in the universe. Yeah, it's
It
when
really
you have to kind of bend your brain a little bit to be thinking about that. But like this Neptune and Triton, they're like right next door. Right, they're part of our solar system, our sun's retinue of planets, and everything else that you see in this image is billions of light years away.
We have Neptune, Triton, 2 stars in our galaxy, and then the universe behind it. It's just like
Backdrop of the universe. Yeah.
What? You're right. Every time we think solar system, we think, okay, there's a planet, and maybe there's a star or two in the background, but we've just never seen just galaxies abundant like this.
That's right. It's a different way of appreciating the scale of the universe. Really, isn't it awesome? It's
a cool universe. I'm glad we're in it.
Yeah, I'm glad we have this brand new tool, James Webb Space Telescope, showing it to us in a different way. And we knew that, we knew that it would do that, but it's different when you see it.
Yeah.
It's amazing.
And now, right now, you're kind of maybe basking in the afterglow of seeing these first images. But as you said, these images of Neptune were made as part of, I guess, the early release observations. Is that right?
No, they were images taken to create beautiful pictures. These were not science targets. This was not part of my program. I have a very large program with James Webb Space Telescope to do solar system science. And certainly the Neptune is part of that, but these are not the science observations. These were taken by folks at the Space Telescope Science Institute just to make pictures to demonstrate the capability of the telescope. And even in the pretty pictures, there's science. There's great science.
Exactly. Right. You can't not, indulge your curiosity, and you can't not notice those incredible details. And what a thrill it must be just to see something new. I mean, certainly to see it in pardon the cliche, a different light, but to see some features that we couldn't really see before. It's just
exactly. I know when I was looking at some of the individual images that went into this with Naomi, and she said, "Look at this here. What is that?" I'm like, "Naomi, I don't know, because we've never seen anything like that before. That's exploration. That's the science that we're going to do, and that's just in these pretty pictures. So when we get our detailed science images that were, planned specifically for science, it's going to be a bonanza. I'm just this whets our appetite for what we're going to get, and I'm really excited about it.